So today we're going to continue our discussion of sequences, mathematical induction, and recursion. With mathematical induction part 1, proving formulas. Okay. In natural science classes, deduction and induction are presented as alternative modes of thought. Deduction being to infer a conclusion from general principles using the laws of logical reasoning, and induction being to enunciate a general principle after observing it to hold in a large number of specific instances. The discovery of new mathematical facts often occurs through experimentation with examples, but mathematical induction as a proof technique is not inductive but deductive. Once proved by mathematical induction, a theorem is known just as certainly as if it were proved by any other mathematical method. The principle of mathematical induction: let P of n be a property that is defined for integers n and let a be a fixed integer. Suppose that the following two statements are true. P of a is true, and for every integer k greater than or equal to a, if P of k is true, then P of k plus 1 is true. Then the statement for every integer n greater than or equal to a, P of n is true. First known use of mathematical induction occurs in the works of Italian scientist Francesco Moralico in 1575. In 1653, Pascal gave a clear description of the technique. In 1883, Augustus de Morgan also gave the process the name mathematical induction. An equivalent logical inference rule known as the well-ordering principle. To visualize the idea of mathematical induction, imagine an infinite collection of dominoes positioned one behind the other in such a way that if any given domino falls backward, it will make the one behind it fall backward as well. Then imagine the first domino falls backwards. Well, then they all fall down. If the kth domino falls backward, it pushes the k plus 1 domino backward as well. To see the connection between this image and the principle of mathematical induction, let P of n be the sentence, the nth domino falls backwards. It is given that for each k greater than or equal to 1, if P of k is true, the kth domino falls backwards, then P of k plus 1 is also true. It is also given that P of 1 is true, the first domino falls. Thus, by the principle of mathematical induction, P of n, the nth domino falls backwards, is true for every integer greater than or equal n greater than or equal to 1. Proving a statement by mathematical induction is a two-step process. The first step is called the basis step. The second step is called the inductive step. Consider a statement of the form, for every integer n greater than or equal to a property P of n is true. To prove such a statement, perform the following two steps. First, show that P of a is true. Then, that's the basis step. Then the inductive step is to show that for every integer k greater than or equal to a, if k is true, then P of k plus 1 is true. To perform this step, suppose that P of k is true, where k is any particular but arbitrarily chosen integer with k greater than or equal to a. This supposition is called the inductive hypothesis. Then show that P of k plus 1 is also true. So use mathematical induction to prove that 1 plus 2 plus 3 plus 4, etc. to n equals n times n plus 1 all over 2 for every integer n greater than or equal to 1. Well, to construct a proof by induction, you must first identify the property n. In this case, the property p of n. In this case, p of n is the equation given on the previous slide. Note the property is just the equation. The proof will show that the equation is true for every integer n greater than or equal to 1. Yeah. In the basis step of the proof, you must show that the property is true for n equals 1. Or in other words, that p of n, or p of 1 is true. Now, p of n is obtained by substituting 1 in place of n in p of n. The left-hand side of p of 1 is the sum of all successive integers starting at 1 and ending at 1, and is therefore just 1. So just to write p of 1, just copy p of n and replace each n by 1. Thus, p of n, or p of 1 is 1 equals 1 times 1 plus 1 all over 2. Of course, this equation is true because the right-hand side is 1 equals 1 as well. In the inductive step, you assume that p of k is true for a particular but arbitrarily chosen integer k with k greater than or equal to 1. That's the inductive hypothesis. You must then show that p of k plus 1 is true. What are p of k and p of k plus 1? Now, p of k is obtained by substituting k for every n in p of n. And p of k plus 1 is substituting the quantity k plus 1 for every n that appears in p of n. Thus, p of k plus 1 is k plus 1 times the quantity k plus 1 all over 2. Or equivalently, k plus 1 times k plus 2 all over 2. Now, the inductive hypothesis is the supposition that p of k is true. How can this supposition be used to show that p of k plus 1 is true? P of k plus 1 is an equation, and the truth of an equation can be shown in a variety of ways. One of the most straightforward is to use the inductive hypothesis along with algebra and other known facts to separately transform the left-hand side and right-hand sides until you see that they are the same. In the case of the left-hand side of p of k plus 1, it's 1 plus 2 plus 3, etc. to k plus 1, which equals to 1 plus 2 plus 3, etc. to plus k plus 1. The last term is k because the terms of successive integers, and the last term is k plus 1. By substitution from the inductive hypothesis, 1 plus 2 plus 3, etc. to plus k is equal to k times k plus 1 over 2. Since the inductive hypothesis says that 1 plus 2 plus 3, etc. to k is equal to k times k plus 1 over 2. Then doing some algebra, you get to k squared plus 3k plus 2 over 2. So the left-hand side of the equation is k squared plus 3k plus 2 over 2. Now the right-hand side of p of k plus 1 is k plus 1 times k plus 2 equals k squared plus 3k plus 2 by multiplying out the numerator. Thus, the two sides of p of k plus 1 are equal to each other, and so the equation p of k plus 1 is true. So the sum of first n integers is n times n plus 1 over 2. Definition. If a sum with a variable number of terms is shown to equal an expression that does not contain either an ellipsis or a summation symbol, we say that the sum is written in closed form. So, applying the formula for the sum of first n integers, evaluate these equations. Well, just multiply things out. This would be, A would be 2 times the quantity n times n plus 1 over 2, with the n equaling 250, I believe. Yeah. So you get 62,750. And and the second one by subtracting a sequence from the previous sequence. And the third one, just some algebraic manipulation. Another famous and important formula in mathematics, the formula for the sum of a geometric sequence. In a geometric sequence, each term is obtained from the preceding one by multiplying by a constant factor. If the first term is 1 and the constant factor is r, then the sequence is 1, r, r squared, r cubed, etc. to rn. The sum of the first n terms of the sequence is given by the formula. The summation is equal to r to the r plus, equals r to the n plus 1 minus 1 all over r minus 1 for every integer n greater than or equal to 0 and every real number r not equal to 1. The expanded formula is given here because r to the 0th power is 1 and r to the first is r. The formula for n greater than or equal to be 1 can be rewritten as this. So, in some mathematical context, 0 to the 0 is regarded as indeterminate. In discrete mathematics, we usually define 0 to the 0th power is equal to 1, so that when we do the summation, we do not need to give special attention to case r equals 0. prove that the summation of r to the I from I equals 0 to n equals r to the n plus 1 minus 1 all over r minus 1 for every integer n greater than or equal to 0 and every real number except 1. In this example, the property, the P of n, is again an equation, although in this case it contains a real variable r. Because r can be any real number other than 1, the proof begins by supposing that r is a particular but arbitrarily chosen real number not equal to 1. Then the proof continues by mathematical induction on n, starting with n equals 0. In the basis step, we show that P of 0 is true. That is, we show that the property is true for n equals 0. So you substitute 0 for each n, and in the inductive step, you suppose k is any integer with k greater than or equal to 0, for which P of k is true. That is, you suppose the property is true for n equals k. So you substitute k for each n in P of n. So there's your inductive hypothesis. Then show that P of k is true. That is, you show the property is true for n equals k plus 1. So you substitute k plus 1 for each n in P of n. So algebraically, you can show it this way. Here. And the sum, and you do some algebraic wizardry, and you come up with theorem 522 for any real number r except 1 and any integer n greater than or equal to 0. That summation is equal to this quotient here. Proving an equality. The proofs of the basis and inductive steps illustrate two different ways to show that an equation is true. Transforming the left-hand side and the right-hand side independently until they are seen to be equal. And two, transforming one side of the equation until it is seen to be the same as the other side of the equation. Sometimes people use a method that they believe proves equality but is actually invalid. For example, to prove the basis step for 522, they perform the following steps. Yeah. Does that work? Well, does it? Deducing additional formulas. Well, the formula for the sum of a geometric sequence can be thought of as a family of different formulas in R, one for each real number R except 1. In each of A and B below, assume that m is an integer that is greater than or equal to 3. Write each of the sums in closed form. Now, you can do applying the formula for the sum of the geometric sequence with r equals 3 and n equals m minus 2. And factor out 3 squared in the second one, and you get this equation here with from part A. As with the formula for the sum of first n integers, there's a way to think of the formula for the sum of the terms of a geometric sequence that makes it simple but and intuitive. If let S of n be the geometric sequence, then R times S of n sub n equals R plus R squared plus R cubed, etc., to R to the n plus 1. And so R to the R times S sub n minus S sub n is equal to R to the n plus 1 minus 1. So yeah. Now R of S, or R times S of sub n minus S sub n equals R minus 1 times S sub n. Equating the right sides of the formula of the equations 521 and 522 and dividing by R1 gives S sub n equals R to the n plus 1 minus 1 all over R minus 1. And that will be it for that section. We'll go on to Mathematical Induction Part 2, Applications. In this section, we will show how to apply it in a broader variety of situations. As a first example, consider the argument that the US penny should be eliminated because it isn't profitable to produce. Due to inflation and the rising cost of metals, it actually costs more than 1 cent to produce a penny. If the penny were eliminated and another coin worth 3 cents were introduced, what prices could be paid using only 3 and 5 cent coins? Show some examples here. 3 cents, 5 cents, 8 cents, 9 cents, 10 cents, 11, 12, 13, 14, 15, etc. For every integer n greater than or equal to 8, n cents can be obtained using 3 and 5 cent coins. Well, use mathematical induction to prove that for each integer n greater than 2, n to the 2 to the 2n minus 1 is divisible by 3. All right. As in the previous proofs by mathematical induction, you need to identify property P of n. In this example, P of n is the sentence 2 to the 2n minus 1 is divisible by 3. By substitution, the statement for the basis step, P of 0, is equal to, or is 2 to the 2 times 0 power minus 1 is divisible by 3. So the supposition for the inductive step, P of k is 2 to the 2k minus 1 is divisible by 3. And the conclusion to be shown is 2 to the 2k plus 1 minus 1 is divisible by 3. Recall that an integer m is divisible by 3 if and only if m equals 3r for some integer r. Now the statement p of 0 is true because 2 to the 0 minus 1 is 0, and which is divisible by 3 because 0 is 3 times 0. To prove the inductive step, you suppose that k is any integer greater than or equal to 0, such that p of k is true. In other words, you suppose that 2 to the 2k is divisible, or minus 1 is divisible by 3. And then you must prove the truth of p of k plus 1, p of k plus 1. Thus, you must show that 2 to the 2k plus 1 plus or minus 1 is divisible by 3. So now you have 2 to the 2k plus 1 is equal to 2 to the 2k times 4 minus 1. Now, your aim is to show that 2 to the 2k times 4 minus 1 is divisible by 3. But why should that be so? Both 2 to the 2k times 4 and 2 to minus 1 and 2 to the 2k minus 1 have a lot in common, but by the inductive hypothesis, 2 to the 2k minus 1 is divisible by 3. Observe what happens when you subtract 2 to the 2k minus 1 from 2 to the 2k times 4 minus 1. You get 2 to the 2k times 3, which is divisible by 3 because it has 3 as a factor. Adding 2 to the 2k minus 1 to both sides, you have those two little terms here. 2 to the 2k times 3, which is divisible by 3. And 2 to the 2k minus 1 is divisible by 3 by the inductive hypothesis. So if the sum of two numbers that are divisible by 3 is both terms of the sum on the right side of this equation are divisible by 3, hence the sum is divisible by 3. Therefore, the left-hand side of the equation is also divisible by 3, which is what was to be shown. So for every integer n greater than or equal to 0, 2 to the 2n minus 1 is divisible by 3. So how about an inequality? Use mathematical induction to prove that for each integer n greater than 3, n squared plus 1 is less than 2 to the n. I'm sorry, 2 to the n plus 1 is less than 2 to the n. Yeah? So in this example, the property is the inequality. By substitution, P of 3 is 2, okay, that's a typo. I forgot about that. Yeah, this is supposed to be 2n plus 1 is less than 2 to the n. So now here they have it right. 2n plus 1 is less than 2 to the n. By substitution, the statement for the basis step, p of 3, is 2 times 3 plus 1 is less than 2 to the 3, which is the basis step. The supposition for the inductive step, p of k, is 2k plus 1 is less than 2 to the k. That's the inductive hypothesis. And the conclusion to be shown is 2 times k plus 1 is less than 2 to the k plus 1. To prove the basis step, observe that the statement p of 3 is true because 2 times 3 plus 1 equals 7, and 2 to the third is 8, and 7 is less than 8. For the inductive step, you assume the inductive hypothesis for a particular but arbitrarily chosen integer k greater than or equal to 3, that 2k plus 1 is less than 2 to the k. And then you must show that 2k plus 1 is less than 2 to the k plus 1. With inequality proofs, you can often apply the inductive hypothesis at an early stage. In this case, you can substitute the induction hypothesis to obtain this equivalency here. So, yeah. Yeah. At this point, you need to think about your goal. You want the right-hand side of the inequality to be 2 to the k plus 1. Since you already know that 2 times k plus 1 is less than 2k plus 2, an easy way to complete your job would be to show that 2 to the k plus 2 is less than, I think they're getting typos here again. Yeah, 2k, not 2 to the k plus 2. And that's 2. Let's see here. Yeah, they screwing up with the typos and stuff like that. Let's go move on. Leave that one alone. Define a sequence A1, A2, A3, etc. as follows. A1 is 2. AK equals 5. A sub k is 5. A sub k minus 1 for every integer k greater than or equal to 2. What are the first 4 terms of the sequence? It is claimed that for each integer n greater than or equal to 0, the nth term of the sequence has the same values as that given by the formula 2 times 5 to the n minus 1. In other words, the claim is that the terms of the sequence satisfy the equation a sub n equals 2 times 5 to the n minus 1. Is that true? Well, the first few terms are 2, 10, 50, 250. Use mathematical induction to show that every term of the sequence satisfies the equation. Begin by showing that the first term of the sequence satisfies the equation. Then suppose that an arbitrarily chosen term, a sub k, satisfies the equation, and prove that the next term, a sub k plus 1, also satisfies the equation. So, uh, let the sequence be defined by specifying a sub 1 is 2, and a sub k is 5 times a sub k minus 1 for every integer k greater than or equal to 2. And let the property p of n be the equation a sub n equals 2 times 5 to the n minus 1. We will use mathematical induction to prove that for every integer n greater than or equal to 1, p of n is true. First, show that p of 1 is true. Well, p of 1 is true because it's 2 times 5 to the 1 minus 1, or 0, or 2 times 1. And the right side is the left side is true because of is 2 because of the definition of the sequence, and the right side is true by 2 times 5 to the 0 equals 2 times 1, or 2. Thus, the two sides of p of 1 are equal to the same quantity, so p of 1 is true. Show that each integer k is greater than or equal to 1. If p of k is true, then p of k plus 1 is also true. Let k be any integer with k greater than or equal to 1, and suppose that the inductive hypothesis is true. We must show that p of k plus 1 is true. Show that k sub k plus 1 equals 2 times 5 to the k plus 1 minus 1. Or equivalently, a sub k plus 1 equals 2 times 5 to the k. But the left-hand side of the equation is 5a sub k plus 1 minus 1, or just a sub k times 5. By inductive hypothesis, you can substitute and then regroup, and then 2 times 5 to the 2k, which is the right side of p of k plus 1. Since we proved the basis step and the inductive step, we conclude the formula holds for all terms of the sequence. A problem with tromonos. The word polyomino is a generalization of domino. Was introduced in 1954. He and others have proved many interesting properties about them, and they became the basis for a popular computer game called Tetris. You've all heard of Tetris before, right? That's a particular type of polyomino. The ones here are using here are called tromonos, which are 3 attached squares, which can be of 2 types, straight and L-shaped. Call a checkerboard that is formed using m squares on a side an m by m checkerboard. Observe that if one square is removed from a 4 by 4 square checkerboard, the remaining squares can be completely covered by L-shaped tromonos. For instance, a covering for one such board is illustrated in the figure here. Now, for any integer n greater than 1, If 1 square is removed from a 2 to the n by 2 to the n checkerboard, the remaining squares can be completely covered by L-shaped trauma nodes. And that'd be it for that section. I'm wondering. Yeah, we'll try one more section. What the heck? Alright. If the thing wants to cooperate. Alright. Section 4. Strong mathematical induction and the well-ordering principle for the integers. A little bit of a mouthful for this section. Strong mathematical induction is similar to ordinary mathematical induction in that it is a technique for establishing the truth of a sequence of statements about integers. Also, a proof by strong mathematical induction consists of a basis step and an inductive step. However, the basis step may contain several proofs for several initial values. And in the inductive step, the truth for the predicate P of n is assumed not just for one value of n, but for all values through k. And then the truth of P of k plus 1 is proved. So, let P of n be a property that is defined for integers n, and let a and b be fixed integers with a less than or equal to b. Suppose the following two statements are true. P of a plus 1, etc. to P of b are all true. That's the basis step. And then for every integer k greater than b, if P of I is true for each integer I from a through k, then P of k plus 1 is true, the inductive step. Then the statement for every integer n greater than or equal to a, P of n is true. The supposition that P of I is true for each integer I from a through k is called the inductive hypothesis. You can say that by, you can state it by saying that P of a plus 1, etc. to P of k are all true. Applying strong mathematical induction. Divisibility by a prime theorem states that any integer greater than 1 is divisible by a prime number. We prove this theorem using strong mathematical induction. Prove the theorem. Well, the idea for the inductive step is this. If you're given an integer greater than 1 that is not itself prime, then it is a product of two smaller positive integers, each of which is greater than 1. By the inductive hypothesis, you are assuming that each of these smaller integers is divisible by a prime number. And so, by transitivity of divisibility, those prime numbers also divide the integer you started with. Proof by strong mathematical induction. Let the property P of n be the sentence n is divisible by a prime number. Show that P of 2 is true. To establish P of 2, we must show that that n is divisible by a prime number. But this is true because 2 is divisible by 2 and 2 is a prime number. Show that for every integer k greater than or equal to 2, if P of I is true for each integers from 2 through k, then P of k plus 1 is also true. Let k be any integer with k greater than or equal to 2, and suppose that I is divisible by a prime number for each integer I from 2 through k. We must show that k plus 1 is divisible by a prime number. Case 1, k plus 1 is prime. In the case that k plus 1 is divisible by a prime number, namely itself. If k plus 1 is not prime, then k plus 1 equals a times b, where a and b are integers with with a being between 1 and k plus 1, and b being between between 1 and k plus 1. So 2 is less than or equal to a, which is less than or equal to k. And so by inductive hypothesis, a is divisible by a prime number p. In addition, because k plus 1 is the product of a times b, we have that k plus 1 is divisible by a. Hence, since k is plus 1 is divisible by a, and a is divisible by p, by the transitivity of divisibility, k plus 1 is divisible by the prime number p. Therefore, regardless of whether k plus 1 is prime or not, it is divisible by a prime number. So, the given statement is true. Define a sequence S as follows. S sub 0 is 0, S sub 1 is 4, S sub k is 6a sub k minus 1 minus 5a sub k minus 2 for every integer k greater than or equal to 2. Find the first 4 terms of the sequence. It is claimed that for each integer n greater than 0, the nth term of the sequence has the same value as that given by the formula 5 to the n minus 1. In other words, the claim is that all the terms of the sequence satisfy the equation S sub n equals 5 to the n minus 1. So, use the strong mathematical induction to show that it's true. The basic step must show the first 2 terms satisfy it. This is necessary because according to the definition of the sequence, computing values of later terms requires knowing the values of the 2 previous terms. So if the basis step only shows that the first term satisfies the equation, it would not be possible to use the inductive step to deduce that the second term satisfies the equation. In the inductive step, you suppose that for any arbitrarily chosen integer k greater than or equal to 1, all the terms of the sequence from S0 through Sk satisfy the given equation, and then deduce that S sub k plus 1 must also satisfy the equation. Proof. Yeah. Just restating the definition here. Use strong mathematical induction to prove it. First, show P of 0 and P of 1 are true. Do that by simple substitution. Then by definition, we have S sub 0 and S sub 1. So we have these to be true. Now show that for every integer k greater than 1, or greater than or equal to 1, if P of I is true for each integer from 0 through k, then P of k plus 1 is also true. Let k be any integer with k greater than or equal to 1, and suppose that s sub I equals 5 to the I minus 1 for each integer I, with I being less than or equal to k but greater than or equal to 0. That would be the inductive hypothesis. Now show that s sub k plus 1 equals 5 to the k plus 1 minus 1. But since k is greater than or equal to 1, we have that k plus 1 is greater than or equal to 2. So s sub k plus 1 equals 6s sub k minus 5s sub k minus 1. And by substituting the definition hypothesis, the inductive hypothesis from the definition, multiplying out and applying the law of exponents, factoring out 6 and doing some arithmetic, you get 5 times 5 k to the k minus 1, or 5 times k plus 1 by applying the law of exponents. This was to be shown. Since we have proved both the basis and the inductive step, we conclude that this given statement is true. Another sequence. This one's using the floor function. A sub k equals 3a sub the floor of k minus over 2 plus 2. Prove that a sub n is for every integer is even for every integer n greater than 1, greater than or equal to 1. Well, first few terms are going to be 0, 2, 2, 8, 8, 8, 8. Let the property P of n be the statement A of n is even. A sub n is even. And use strong mathematical induction to show that the property holds true for every integer n greater than or equal to 1. Well, show that the properties are, show that P of 1 and 2 are true. This property is true for n minus 1, n equals 1 and 2 because a sub 1 and a sub 2 are 0 and 2 respectively, and they are both even. Show that every integer case is greater than or equal to 1. If P of I is true for each integer from 1 through k, then P of k plus 1 is also true. Let k be any integer with k greater than or equal to 1, and suppose that a sub I is even for each integer with 1 for each integer I, with I being greater than or equal to 1 or less than and less than or equal to k. That's your inductive hypothesis. We must show that a sub k is even. Well, by the definition, we have this. Now, a sub floor of k over 2 is even by the inductive hypothesis because k is greater than 1 and or equal to 1. So 1 is less than or equal to a sub k, the floor of k over 2 is less than or equal to k. Thus, 3a is even because it is a product of an even and an odd integer. Hence, 3a sub floor of k over 2 plus 2 is even because a sum of two even integers is even. Consequently, a sub k, which equals to this, is even, as was to be shown. So the given statement is true. Convention. Let us agree to say that a single number x sub 1 is a product with one factor and can be computed with 0 multiplications. Prove that for any integer n greater than or equal to 1, if x sub 1, sub 2, sub 3, etc. to x sub n are n numbers, then no matter how the parentheses are inserted into their product, the number of multiplications used to compute the product is n minus 1. So, the truth of the basis step follows immediately from the convention about a product with one factor. The inductive step is based on the fact that when several numbers are multiplied together, each step of the process involves multiplying two individual quantities. For instance, the final step for computing this here is to multiply x sub 1 times x sub 2 times x sub 3 and x sub 4 times x sub 5. In general, when k plus 1 numbers are multiplied, two quantities in the final step each consist of fewer than k plus 1 factors. This is what makes it possible to use the inductive hypothesis. So the proof that P of n be the sentence that we went through earlier. Show that P of 1 is true. Number of multiplications needed to compute a product of 1 is 1 minus 1 or 0. Because it's true because of by convention x sub 1 is a product that can be computed with 0 multiplications. And 0 equals 1 minus 1. Now for every integer k greater than 1 or equal to 1, if P of I is true for each integer from each integer I from 1 to k, then P of k plus 1 is also true. Let k be in any integer with k greater than or equal to 1, and suppose that for each integer I from 1 through k, if x sub 1, x sub 2, etc. to x sub I are numbers, then no matter how parentheses are inserted into their product, the number of multiplications used to compute the product is I sub minus 1. All right. So if those are the numbers and our k plus 1 numbers, then the multiplications used to compute the net product is k plus 1 minus 1, or k. Consider a product of k plus 1 factors. When parentheses are inserted in order to compute the product, some multiplication is the final one, and each one of the two factors making up the final multiplication is a product of fewer than k plus 1 factors. Let L be the product of the left-hand factors and R be the product of the right-hand factors. And suppose that L is composed of I factors and R is composed of of little l factors, and R is composed of little r factors. Then little l plus little r equals k plus 1, the total number of factors in the product. By inductive hypothesis, evaluating big L takes L minus 1 multiplications, and evaluating big R takes little r minus 1 multiplications. Because one final multiplication is needed to evaluate big R, L, and big R, the number of multiplications needed to evaluate the product of all k plus 1 factors is k. So, which was to be shown. So we can conclude that the statement is true. So, the existence and uniqueness of binary integer representations. Given any positive integer n, n has a unique representation in the form here, where r is a non-negative integer. Cr equals 1, Cj equals 1 or 0, for each j equals 0, 1, 2, 3, etc. to r minus 1. So, yeah, each positive integer has a unique binary representation. The well-ordering principle for the integers. The well-ordering principle for integers looks very different from both the ordinary and the strong principles of mathematical inductions, but it can be shown that all three principles are equivalent. In other words, if any one of the three is true, then so are both of the others. So, the well-ordering principle for the integers, let S be a set of integers containing one or more integers, all of which are greater than some fixed integer, then S has a least element. Kind of a common sense thing there. Finding least elements. If the set has a least element, state what it is. If not, explain why the well-ordering principle is not violated. The set of all positive real numbers. Well, it has to have a least element. They're all positive, so the number 1. But this only applies to real for integers, so positive real numbers. It doesn't violate it. The set of all non-negative integers n such that n squared is less than n. Non-negative integers such that n squared is less than n. Is that possible? Be the empty set, wouldn't it? So it doesn't violate the well-ordering principle. The set of all non-negative integers in the form 46 minus 7k, where k is an integer. Now, the smallest one would be 4, I think. Been a semester since I looked at these slides. So. Well, there is no least positive real number. For any x, if x is any real positive number, then x divided by 2 is a positive real number. And that is less than x. No violation of the well-ordered principle occurs because the well-ordering principle refers only to the set of integers. This is not a set of integers. There's no least non-negative integer n such that n squared is less than n, because there is no non-negative integer that satisfies this inequality. The principle is not violated because it only refers to sets that contain at least one element. And it was the empty set, so k equals 6. So values of 46 minus 7k for various values of k. Table suggests you can easily confirm that 46 minus 7k is less than 0 for k greater than 7. And that 46 minus 7k is greater than or equal to 46 for k less than 0. All right. Therefore, from the other values in the table, it is clear that 4 is the least non-negative integer of the form 46 minus 7k that corresponds to k equals 6. Quotient remainder theorem, the existence part. Given any integer n and any positive integer d, there exists integers q and r such that n equals dq plus r. And r is less than d but greater than or equal to 0. And that would be bringing us to the end of the section. Right on time. Okay, we will continue with chapter 5 on Tuesday. In the meantime, have a good weekend and see you next time.